This is Lisa Goss of Idaho State University. This is a screencast version of a talk that I recently gave at Boise State. I want to talk about my experience flipping the physical chemistry lecture course using just-in-time teaching and cooperative learning techniques. The story begins with a comment that I sometimes got from students. It made sense when you explained it in class, but I sat down to do the homework and I don't get it anymore. And even on a day when lecture's going smoothly, the students are nodding and understanding, you can tell by the looks on their faces that they're following what you're saying. Even when you give a great lecture, sometimes we still have students not being able to do the homework. I think this phenomenon is brilliantly summarized by this cartoon by George Cham, referring to the aura of logical distortion. So this cartoon is about the relationship between a research student and that student's research advisor, but I think it applies to a student in a class and the instructor as well. The student is standing next to the instructor. The student says, that totally makes sense. Student understands. Instructor goes away, i.e. lecture is over, and student suddenly finds that, oh wait, it doesn't make sense anymore. And this phenomenon with students in my p-chem class left me wishing that I could clone myself, right? One clone to come to class and give the lecture, and another clone for each student in the class to go home and help the student with the homework, to tutor the student on the homework, in fact. Well, obviously I can't clone myself, but screencasting seemed to me to be the answer to this problem. Instead of me standing up in the front of the room lecturing, and that's all of my time that the students get, I can record my lecture in the form of a screencast. The students can listen to that, watch that before class at home or in a computer lab. Then in class, we can spend our time getting unconfused, understanding topics more deeply, starting to learn to do the problems that constitute the homework. So the question with an approach like this, if you assign these screencasts and tell students to watch them before they come to class, is always, what if the students don't watch the screencast, right? We tell students to read the chapter before we cover it in class, but they don't usually do that. Why would the students watch the screencast before they come to class? So my thinking on this was influenced by a talk given by Julie Schell at FlipCon 2013, and at that time she was working with the Mazur group at Harvard on peer instruction. And she shows a slide with a photograph from a movie, and the quote from the movie is, "If you build it, they will come." But she had crossed that out and written, "If you assess it, they will do it." And that was the approach that she recommended to this problem of students not doing the before class work, was build in the assessment of that before class work. And that's where the just-in-time teaching approach comes in. My thinking on the just-in-time teaching technique was influenced by this text referenced here, and I've drawn this diagram to summarize this process. We'll talk about each of these parts separately, but at this point I want to tell you that the top row is me, the teacher, and the bottom row is the students, and the three different squares refer to three different time periods. So let's look at the first one. So the first thing that happens is that I post the screencast on the learning management system. We use Moodle, so I'll refer to Moodle, but this applies to other systems as well. And then I make a quiz of warm-up questions. So the students are then assigned to watch the screencast and complete the warm-up questions, which are given in the form of a quiz, and they do this before class. This is an example of what one of my screencasts looks like. This is a Mathematica file in the slideshow mode, so it's a slide with text on it, as well as a figure from the book in this case, and they see this on their screen in the video, and they hear my voice, and that's what a screencast looks like. The warm-up question quizzes are generally one question per screencast, plus what we call the muddiest point question, and this is a just-in-time teaching technique. And what I used was this question shown here. Of the material of the screencast, what was the most confusing point? If nothing was confusing, what was the most interesting? One of the things that happens in lecture sometimes is that you can see on the students' faces that they're confused. They're not following what you're saying. And you could ask, okay, are there any questions? And sometimes you'll get a student who will speak up and say, okay, I'm confused about this. And then you can address that point of confusion. And sometimes you'll look out and you see the confused faces, but you can't get a student to ask a question, and so it's hard to figure out in some cases what they're confused about. When you ask a student what was the most confusing thing about the screencast, and the student is asked that question in the privacy of his or her own home, it's amazing the feedback that you get. The feedback that I've gotten on some of the topics in physical chemistry has profoundly impacted the way that I explain some of these concepts. It's very, very useful feedback. So then, 4 hours before class starts, the warm-up question quiz closes. I download the students' answers and look at those. And I decide, okay, based on what the students gave as answers to the questions and based on what they said was the most confusing thing, I decide whether I need to prepare a miniature lecture, an explanation of a topic that they found confusing, if we need to look at something in a different way, or whatever the students' answers indicate to me we need to do. And then I prepare cooperative learning exercises, or CLEs. So then we get to class. If a mini lecture is called for, I start with that. Then we talk about the warm-up questions. And then I hand out the cooperative learning exercises, and the students work on those, and I circulate from student to student, group to group, assisting the students with the cooperative learning exercises while they're working together. And then towards the end of class, I generally have one or more students show their results on the board. So here's an example of a Mathematica file that I used to talk about a warm-up question at the beginning of class. In this case, it's Chapter 29, Topic F. The question is about the Lindemann mechanism, and I just asked them, for which species do we make a steady-state approximation, and what are all of the species in the Lindemann mechanism? And this is one example of an answer here. And I got a muddiest point question about this topic where the student asks, how can a reaction have different orders at different concentrations? And that is the heart of the Lindemann mechanism, is explaining that phenomenon. So asking a simple question about the mechanism that just addressed whether or not the student had watched the screencast set the student up to ask a deeper question about what is really going on here. And so after we talk about each of the warm-up questions, examples of answers, muddiest points that relate to those topics or any topic in general, sometimes we need a mini lecture. Here's an example of a diagram that I drew on the board to help students see the big picture. We have these two models, the rigid rotator and the harmonic oscillator, and we have 3 different types of spectroscopy that we can be analyzing using a combination of these 2 different models. And so by drawing this diagram, I was able to help the students see how these smaller concepts explain these bigger ideas. So after talking about the warm-up questions, doing any mini lectures that we need, the students turn their desks to face each other in groups, and I go from group to group, student to student, working with them, coaching them, or tutoring them on those cooperative learning exercises. So my thinking on cooperative learning was influenced by this textbook here. They give a 5-part definition for cooperative learning: small group learning, cooperative behavior, individual accountability and responsibility, and interdependence. I'm not going to talk about those 4. What I want to focus on is learning activity suitable for group work, because that's where it really gets interesting in terms of applying cooperative learning to physical chemistry. So one type of cooperative learning exercise that I give is just simple numerical calculations. In this problem, I give the students some information and ask them to calculate the heat, the work, and the internal energy change. One of the challenges in physical chemistry, according to the students, is how do I know which equation to use? Dr. Goss, there are 80 equations in this chapter. I don't know which one to use. And so by doing simple numerical calculations in class, I can set the students up to succeed with more challenging numerical calculations in the homework, because we can spend time talking about how do you know which equation to use? Which equation goes with which words? Which sets of conditions do we use each equation for? Sometimes I just have to point them in the right direction. Sometimes I kind of have to nudge them in the right direction. And sometimes we're just confused and I have to drag them kicking and screaming from one section of the book to a different section of the book. But we do that in class where I can coach them and I can get immediate feedback on, do they understand what I'm asking? Do they understand how it relates to the concepts that I introduced in the screencast? And what questions do they have? Sometimes cooperative learning exercises are qualitative problems. This problem is about standard molar entropies. I gave them some formulas and some structural information and a bunch of numbers. And I told them to draw Lewis structures and then describe what you see in these numbers and describe any any differences or trends that you can observe? And this is a qualitative problem that asks them to make sense of differences in structure and how that affects standard molar entropy. Sometimes we do things that are just downright strange. One of the topics that we talk about a lot in the quantum chemistry section is the concept of separation of variables, where we take a partial differential equation and separate it into two or more ordinary differential equations in order to solve them. And to help students get a handle on this technique, I gave them a piece of bright pink paper, a piece of paper that I had printed out equations on, a pair of scissors, and a glue stick. And I said, okay, cut these equations apart and arrange them on this pink sheet in a way that reflects how they are related, and then draw arrows showing what goes to where, and label those arrows with how you get from one equation to the next equation. Here's a close-up of part of it, so you can see our starting equation up at the top. To get from the top one to the middle one, they had to make an assumption, and they've written that on next to the arrow, and then there's the actual separation part. In this case, we were using class time for a physical hands-on activity where we could see the separation of variables ripping the differential equation apart in order to solve it. Here's another example of a cooperative learning exercise. This is what I like to think of as an organization exercise. These are different parts of the molecular partition function for different classes of ideal gases. And when we go through the screencast, we meet these equations as if we're going across this table in rows. But when we get to class and I tell them to fill in the boxes and then look at the columns, they can see how these things are related to each other. It turns out the only difference in all these different entries in the first column is what we use for the mass. And the only difference in the vibrational column, the third column, is how many vibrations. And the reason we have 6 different rows in this table is really because of the rotations. When we go through the screencast and we meet these concepts one at a time, it's difficult to see that big picture, but when we get to class and we do an exercise like this, it's much easier to see the big picture, to see how all these tiny little parts relate to each other. Sometimes I give them plain old calculus problems. By the time we get to this equation, in the spring semester, it just echoes through the rest of the course. We use it over and over and over for several chapters. In order to make sure that students have a handle on what this equation is and where it comes from, I have them derive it. I give them the starting point, I give them the ending point, and to do this, you just need to integrate 1 over pressure with respect to pressure. It's not difficult calculus, but by making them do it by hand in class, they have an appreciation for what this equation really means. But that leads us into another problem that students have with physical chemistry. I don't remember how to integrate 1 over pressure with respect to pressure. It's been 3 years since I took calculus. Or, I didn't do very well in calculus. I don't remember how to do this. Physical chemistry has a lot of calculus and algebra to go along with it. And for some students, that's fine, but for many students, this is a challenge. Not only do they have to have taken and passed the class, but they actually have to understand and apply and use skills that they learned in calculus. So one approach to dealing with the algebra and calculus challenge in physical chemistry is to use a symbolic math program. And to illustrate the usefulness of a symbolic math program, I want to talk a little bit about the radial distribution function and the most probable radius. So what do I mean by a symbolic math program? The one that we currently use at ISU is Mathematica. I have previously used Maple. Other examples are things like Sage or MATLAB. So a symbolic math program allows you to do math symbolically. When we talk about the sizes of orbitals in general chemistry, we tell students that as the n quantum number gets bigger, the orbitals get bigger. A 2s is bigger than a 1s, a 3s is bigger than a 2s. Well, the radial distribution function has a slightly different form for each of those orbitals, and it describes the radial distribution of the probability. To get the radial distribution function p, we need the radial part of the atomic orbital, and we can characterize the size of an orbital by looking at something called the most probable radius. That's the radius at which the p function has its highest value. And to find that most probable radius, all you need to do is take the derivative of the p function with respect to r, set that derivative equal to 0, and solve for the value of r that makes that derivative 0, right? It's finding the maximum of a function, an important and elementary calculus concept. You can get a lot of the same information by simply drawing a graph of p of r. Here I've graphed p of r for The red line is a 1s orbital, the blue line is a 2s, and the purple line is a 3s. And you can see that as we go from red to blue to purple, the radius at which the p of r function reaches its maximum increases, and that's the increasing size from 1s to 2s to 3s. Well, these p of r functions for a 1s, 2s, and 3s become more and more complicated. So to take the derivative of any of these, set it equal to 0, and solve for the most probable radius becomes quite challenging by the time you get to a 3s atomic orbital. A textbook that I used to use actually asks students to do this in an end of the chapter problem. And in order to solve that equation for r, for the most probable radius, the solutions manual actually indicates that polynomial long division is required. And that's actually a real thing, polynomial long division. I went back to my calculus textbook and found it. And I only assigned that problem once because that's not the kind of thing that students are going to learn from when they do it by hand. Right? It's just applied math. In Mathematica or another symbolic math program, that same problem becomes quite manageable. Here's an example of the Mathematica code. I have defined a p function. I have used n is 1 and L is 0 to get a 1s orbital. I take the derivative of that p function with respect to r, set that derivative equal to 0, and the only complicated thing about doing this in Mathematica is figuring out which of the solving functions to use. In this case, it's actually the reduce that we want. And you get two answers for where the derivative is 0, and by inspecting a plot, you can determine that the 52.9 picometers is the most probable radius for a 1s orbital. So teaching the students in a physical chemistry class to use a symbolic math program to do the algebra and calculus can save them significant amounts of time and frustration that they might otherwise spend finding results by hand with paper and pencil when doing homework. But the challenge about using a symbolic math program is that the students may save time doing the algebra and calculus, but they may also lose time learning to use the program, finding typos when they're using the program, and just getting familiar and managing the syntax that's required to use these symbolic math programs. And so that brings us to another issue that physical chemistry students have. Mathematica won't calculate this for me, and I don't know what the problem is. I know I'm supposed to calculate this thing in Mathematica, but I've got this error message, and I don't know how to fix it. Well, coupling the use of the symbolic math program with screencasting has led me to some interesting conclusions. It turns out that by requiring students to reproduce Mathematica work that I do in the screencast, they build their skills with Mathematica to a degree where they don't have that same time cost associated with finding typos and syntax problems. So the first step is that in the screencast, I do something in Mathematica, and the screencast captures that. And then when the students watch that screencast, what they are to do is to open the starting Mathematica file and follow along. So here's what that looks like. Here is a screencast, and the student is about halfway through. And in that screencast, I am doing a calculation in Mathematica. These are the inputs, and here are the outputs down here. The student then opens the file, the same file that I started with, they have available to start with, and the student is then working to reproduce in his or her own file what I did and showed in the screencast. Most of the time, students are able to reproduce what I did without too much problems. But since they do this before class, I ask them to then email me their file before class as one of the warm-up questions, and I can then look at those before class and figure out, are there any problems? If so, what was the problem? And here's an example of a problem that a student had that student wasn't able to resolve, but which I talked about in class. The student was doing this calculation, and these two epsilons are supposed to ratio out, right? They're supposed to ratio out. The answer that we're after is actually the minus 0.424 answer. It wasn't until I blew this up to 200% on my screen that I realized the reason they weren't ratioing out is that in one place the student had typed a curly epsilon, and in another place the student had typed a regular epsilon. And those are not the same thing, and so they didn't ratio out, right? So we spent a little bit of class time looking at the work that we had done in the screencast and addressing any problems that the students had. Step 2 then is that when I give the students a homework assignment, I can give them problems problems which are closely related to things that we did in the screencast, and they can do those problems by starting with the work that they did in reproducing the screencast and adapting it to a similar problem. And then after that, I can also give them problems which build on those concepts but don't use the same starting point. For example, here we're applying the variational method to a harmonic oscillator, whereas in the screencast and in the first homework problem, we were applying it to a hydrogen atom. And so this three-step process where the first thing students do is reproduce what I do in the screencast. The second thing they do is adapt it to a new problem. And the third thing they do is do a completely different kind of problem about the same concept. That three-step process builds their skill with the symbolic math program to the point where they become quite competent, but without spending hours and hours chasing typos and looking for syntax problems or trying to figure out syntax problems. So by the time we get to chapter 10, we can do some interesting things. These are the linear combinations for the sp3 hybrid orbitals. And I remember meeting sp3 hybrid orbitals as a general chemistry student. My instructor explained it in a way that made it sound like paint mixing, right? You take a 2s, you take a 2px, and you mix them together and you get this hybrid orbital. Or you take four things and you mix them together and get hybrid orbitals. And I thought about it like red paint and blue paint gives you purple paint. Well, by the time we meet this, the students know how to, number one, get a 2s orbital, how to get a 2px, y, or z orbital, and they know how to draw graphs, three-dimensional graphs of those orbitals. So I show the students the process for the sp hybrids, but then I say for the sp2s and sp3s, find the linear combinations in your book, make those linear combinations, and draw pictures of them. And so where that leads us then is to pictures like this for the sp3 hybrids that the students have drawn from the actual wave functions. No mixing metaphor is needed here. The students can see, okay, we start with these solutions to the hydrogen atom, and we take these linear combinations and we draw pictures of them, and what comes out of those linear combinations is four things that have the same shape but different orientations, and we get those different orientations by changing the linear combinations of the different p orbitals. So by introducing mathematical work in the screencast and asking the students to, it seems like, oh, you're just asking them to reproduce what you do in the screencast. It seems like that would be tedious and not helpful. But it's not as tedious as I would have originally guessed. The students sometimes find it challenging. They can watch the screencast, but they have to type the input commands themselves, and that typing of those commands with no typos and no syntax problems, that builds their skill. That does not solve all of our problems, however, in physical chemistry. Even with screencasting, even with a symbolic math program, I still have students say to me, I have no idea how to start this homework problem. Right? There are still some problems that they just feel lost on. I love this cartoon because it really captures the feeling that some students have. I can see on their faces that they're just completely lost. Can you say that again? But what I am seeing now with the use of screencast before class, warm-up questions before class, cooperative learning exercises in class, and then homework that builds on those cooperative learning exercises that we did in class, what I'm seeing now is that the times when students are lost are the times when I have not built in that step-by-step structure. We meet the concepts in the screencast, we explore and get unconfused on the concepts in class, and then the homework problems build on the in-class exercises. When one step out of that is missing, that's when students say to me, I don't know what to do. And so my current challenge is working on the places in my courses where one of those steps is missing, where we don't have that nice smooth progression from meet the concept in the screencast, answer a warm-up question about the concept, come to class, talk about the concept, do exercises on that concept, and then go to the homework and really dig into applying that concept. So here are my key lessons from my experience applying just-in-time teaching and cooperative learning activities to my physical chemistry course. When you move the introduction of content out of class time and into screencasts, that frees up most of your class for cooperative learning exercises. And this was actually one of the drivers, one of the things that drove me to try flipping my p-chem class the first time, is I'd been trying to cram cooperative learning exercises into class time for years, but the lecture ate up too much of the time, right? So if we move the lecture out of the class time and into the screencast, that gives us lots of class time for active learning to happen. The wide variety of different types of material in physical chemistry leads to a wide variety of different types of cooperative learning exercises. I've shown you some examples of the cooperative learning exercises, but the key here is to really focus on matching the exercise to the topic or to the concept. I have found that following examples in screencasts build student experience with the Symbolic math program, and they lose less time to finding and fixing typos and syntax errors. They build up their own input commands in a way that they can then use those in doing homework problems. And finally, cooperative learning activities done in class allow me to coach the students. I can really get in there and help them with the parts where they are having difficulty, and that sets up this progression from meeting the concept in the screencast, exploring it in class, and then being prepared to do that, to really dig into that concept on the homework. There are some challenges that I continue to work on. Nothing that I have talked about in this talk is in any way educational research. These are just my observations of what I'm seeing in my own classroom. Nothing that I'm doing here changes the fact that physical chemistry contains some conceptually very difficult material. This is difficult stuff for chemistry majors, particularly those who became chemistry majors because of working with molecules in organic. The material in physical chemistry can be very challenging for some types of chemistry majors. Another challenge that I have come to really appreciate is the scope of what we think constitutes the modern physical chemistry course. There is a huge amount of material in this course. I have thrown out many topics. I need to throw out more topics in order to make it not so much a fire hose of a course. And finally, I am working on this progression from meeting this concept in a screencast, exploring it in the cooperative learning exercises, and then really digging into it on the homework. There are places in my course where this is already built in and it works great, and there are places in my course where I really need to beef up this stepwise building that leads to students having a positive experience in the course. Here's my email address down at the bottom. I'd be happy to take questions by email about this talk.